Thanks, Sissy, for the great introductions and of course, as John was alluding to earlier, for really coordinating and organising this event which got us all here. I was really excited to come that 6 months ago. I made the trip halfway to California to start a sabbatical, so it's good to get over here to the East Coast finally after half a year. So I've got the somewhat Herculean task of giving enough of an introduction in this first 25 minutes that John and Alan and Tom can then talk in a little bit more detail about some of the aspects. And so, as Sissy mentioned, while most of the lessons that we've learned that we'll try and share with you today are from the earthquakes in 2010 and 2011 in the Christchurch region, in November last year there was, of course, the Kaikoura earthquake as well. And I think differentiating between those two is really nice because there's a few clear distinctions, and I'll try and touch on those in terms of lessons and how they might apply to the New York and Northeast area as well. So the talk I'll give will really be based around two main parts. First, I'll begin. Sure. Thank you. Usually I have a pretty loud voice, but I'll give one slide on overviewing New Zealand just for those that are not too familiar with it, and then really talk first about the Canterbury earthquakes, and then secondly about the Kaikoura earthquakes. And as I mentioned, just focus on a couple of key aspects there that might be of particular interest to you, because while every earthquake teaches us many things, there are obviously a few that are of particular interest. So for those that are not familiar, this is New Zealand in the southern hemisphere of the world, and the image that we've got on the left and the right show the tectonic activity in terms of recent earthquakes in the region. In particular, the image on the left-hand side is colour-coded based on the depth of those earthquakes, and the image on the right-hand side indicates the main sort of fault structures in the region. The most important thing to understand about New Zealand tectonics is that in the northeast of the North Island, we have subduction of the Pacific Plate below the Australian plate. In the southwest of the South Island, the sense of subduction is reversed, where now the Australian plate dips beneath the Pacific Plate. And as a result of that, we get a large amount of shallow crustal earthquakes in the top 15 to 20 kilometres throughout most of New Zealand. So as you can see from that image on the left, we can really get earthquakes anywhere, although obviously some portions of the country are more susceptible to earthquakes than others. For context, the Canterbury earthquakes lie here on the east coast of the South Island, about halfway in the latitude direction, and the proximal region of the 2016 Kaikoura earthquakes was in the upper half of that South Island along the eastern seaboard. The main thing to point out at this stage, which I'll try and touch on a little bit more, is the location of the Canterbury earthquakes was really in an area of moderate to low seismicity by New Zealand standards, not too dissimilar to the east coast of the US, whereas the Kaikoura earthquake was in one of our highest seismicity areas of New Zealand. So just to follow on that idea a little bit more about the known earthquake activity in the Canterbury region, this is a zoom in of that portion there. You can see all the different coloured lines there representing mapped faults throughout the region, whereas Christchurch City, located here right on the Pacific Ocean, actually didn't have any mapped fault structures immediately beside it. And that was largely because of the recognition that there's several hundred metres to kilometres in some locations of sediments that Christchurch sits on, and therefore it's very hard for us to actually identify the fault structures. So you can see here this magenta coloured line, which indicates the location of the first earthquake that really started the sequence in 2010, and then progressively over time we saw this sequence move generally in an easterly direction. So this is sort of an illustration of how things changed with time. We had that first earthquake located here, and then a significant amount of aftershock activity. Obviously, after several months, that aftershock activity died down. In the next month and a half, it was relatively low. Then we had the most devastating earthquake in the sequence, the 22nd of February 2011 Christchurch earthquake, and then, of course, a large amount of aftershocks associated with that. The important thing with that latter earthquake was that while it was smaller in magnitude, its location relative to Christchurch City meant that it caused much stronger ground shaking in the city itself. The sequence continued a few months later, approximately 6 after that. There was another magnitude 6.0 earthquake, what we often colloquially refer to as the June 2011 earthquake, and then about another 6 months later we had a magnitude 5.9 earthquake. This image is illustrating the location of the February 22nd 2011 earthquake, shown by this rectangle here, and then the waveforms that you can see are the recorded ground motions throughout Christchurch City. So as a sense of scale, the length in terms of width of this image is around about 6 kilometres. So you can see that there's a relatively dense amount of recorded ground motions in that region, and I think this is one of the successes of the Canterbury earthquakes, was a good constraint on what the level of ground shaking was, which then from a reconnaissance perspective allows us to understand the correlation between shaking intensity and consequent damage. As was alluded to earlier, there was a multiple series of earthquakes, and each one of these images is sort of indicating the severity of ground shaking. And I think this multiple events is obviously particularly interesting in our ability to understand at the same set of locations the repeatedness or lack of repetition of seeing certain levels of damage, whether that be in terms of liquefaction or building performance and so on. For some of the slides that I'll present a little bit later, this is just an illustration of the severity of shaking in terms of response spectra in the region. These 4 lines here are 4 instruments located in the Central Business District, or what we refer to as CBD, and then the 2 dashed black lines indicate the 10% in 50-year level of design shaking, and then the MCE, or 2% in 50-year level of shaking. So that first earthquake in September 2010 caused, let's just say, approximately 10% in 50-year ground motions, whereas that event in February 2011, because of its closer proximity, caused shaking similar to the 2% in 50-year design motions. One of the aspects of particular note in terms of ground shaking in the Canterbury region is the sedimentary structure, and I think it's something in terms of site response that is particularly relevant for the New York City area as well. So if we just take a couple of cross sections here through the Christchurch region, here's Christchurch City. We have the mountains to the northeast, and then obviously a large amount of fluvial deposition environments which lead to this deep basin of sediments. So when we take a cross section through here, we see this image on the top panel, where this area is the Banks Peninsula volcanic complex, a 6 million year old volcano. And so then as we move northward from there, you see this thickening of the sediments, and then vice versa, as we move to the west, you see a thickening of the sediments in this direction as well. And so when we look at the ground motions produced as a result of this earthquake, this is the February 2011 earthquake, you see this polarization where the shaking to the north is significantly stronger than it is to the south as a result of this effect of the sedimentary basin. This leads to the trapping of seismic waves, which produces ground shaking that's both stronger and also lasts a lot longer than in more rock-type environments. Liquefaction was obviously a massive issue in the earthquakes, and really I'll just talk with 1 or 2 slides about that because John and Alan and Tom are going to do it more justice than I can. I think the important thing was the severity and the spatial extent of liquefaction in the region. So this slide is illustrating the severity, warmer colours indicating more severe liquefaction, and basically the CBD of Christchurch is pretty much halfway in terms of the east-west extent of the city. So the image that I'm showing here represents somewhere on the order of about 50% of the urban area of Christchurch, and so you can see there from the colours, which are orange or red, that something on the order of about 25% of the whole urban area in Christchurch was significantly affected in one way or another from liquefaction. Obviously that liquefaction had significant impacts for lifelines. This is just illustrating the areas shown as red points where we observed breaks in the water network, and Tom's going to do obviously some more discussions on those particular issues. One of the success stories of the Canterbury earthquakes was the performance of the residential housing stock, with the exception of those structures located in areas with significant liquefaction, such as this one, which obviously as a result of the ground deformation suffered substantial differential settlements. The performance of the timber houses in general was really good, and one of the side effects of that is while people were sometimes living in damaged houses, they could actually shelter in place, and so there wasn't actually a need for temporary housing, and I think that was really a success story, and something which when we move to dense urban areas is obviously becomes more of a problem. Masonry structures, there's not a huge amount of masonry in New Zealand, but we do see it more predominantly in our outside of the main cities in what we'd call provincial New Zealand. I was really interested to see, as I drove from Newark Airport yesterday into New York, that sort of your impression before ever arriving here of skyscrapers everywhere really only applies in the couple of city blocks of Manhattan, and outside that there's obviously a huge amount of masonry structures. So we saw the expected type of performance for a strong level of shaking here, where most masonry walls failed in out-of-plane shaking, and so you can just see a couple of images here representing that. There was also a large amount of retrofits on some masonry structures that were performed, and again, coming back to the idea that the Canterbury earthquakes, we had several episodes of strong shaking, we could actually observe the performance of some of these retrofits over time. So there were a few examples such as this, which initially performed relatively well. You can see here the tie-back anchors in the wall that progressively over the couple of events slowly started to decay. And there was really mixed performance. Some of these really performed quite well and others actually really quite poorly. And so we tended to see this substantially throughout the region. However, there are some really simple retrofits. This is just one example of steel bracing around the side of a substation that performed extremely well throughout the city. And these retrofitted substations are really the majority of masonry buildings that are left in Christchurch now. All the rest of them have been demolished. Probably one of the surprising things, this was sort of Christchurch's version of the 1994 Northridge earthquake phenomena. Northridge was the problem with steel frames and brittle failure of the web. In Christchurch, what we observed was the poor performance of some post-1970 ductile concrete moment frames, where all of laboratory experience, both in New Zealand, also in Japan and the US, tended to indicate that these systems were designed such that we'd get really nice plastic hinges with large amounts of flexural cracking, whereas in a pulse-type earthquake, what we tended to observe was few isolated cracks, and of course, in order to accommodate the same amount of displacement demand in the building, when you have less cracking, you need to have larger strains across those cracks. And so as a result, we observed larger strains in the reinforcement and some very brittle failure of some of those reinforcing bars. Also, a little bit like some observations that we've seen in Chilean earthquakes, we saw some relatively poor performance of slender reinforced concrete walls, particularly those with small amounts of confining steel. And there were two buildings that suffered either partial or complete collapse that I'm showing here on the left-hand side, the Pinegould Guinness building, and on the right-hand side, the CTV or Christchurch Television building. Notably, neither of these buildings were identified as earthquake-prone beforehand, and so that really highlights the fact that some of our sort of first-order evaluation procedures for buildings don't always identify some of these critical vulnerabilities that ultimately lead to collapse. Some of you may be aware that the damage to the Christchurch Central Business District was quite extensive in terms of proportions. This is a view from the nearby Banks Peninsula looking across the city. And in total, somewhere on the order of 70 to 80% of the total floor area in the Christchurch Central Business District has been demolished at this point in time. I chose to use an image here from the end of 2012 just to try and give a bit of an indication that these demolitions obviously didn't happen immediately after the earthquake, that really they've taken 3 or 4 years for some of the negotiations around whether a building is repaired or whether a building is demolished to occur. And so one of the reasons for that, of course, was the discussions between building owners and the insurance contractors. Now, part of the resilience of New Zealand in responding to the Canterbury earthquakes has really been associated with the extremely high insurance penetration that New Zealand has. It's the highest in the world, something on the order of about 80%. And it's mandated for all residential housing to have insurance through this nationalised insurance entity called the Earthquake Commission. And also it's almost universal that private businesses have this insurance as well. So while that's a blessing in some regards, it also caused a significant amount of delay in terms of those negotiations with the insurer. And in particular, there's no legal bound for the amount of time that that negotiation has to go on. So while large private entities might have a lot of resources at their disposal to have those negotiations, obviously you can imagine as an individual resident of a city having negotiations with an insurer is a particularly unbalanced sort of power struggle. And so in mid-2014, which is 3 years after the event, only 80% of the claims had actually been settled, so 20% of people living in broken houses still hadn't had a settlement of their claim with the insurer, and actually documents from the insurers openly disclose that they expect until 2021 to be settling some of these claims, so that's 10 years after the event. This is a couple of snapshots from some newspaper articles which really is highlighting some research that's come out by psychologists over the last few years, which quite clearly through different authored reports indicates that for many people the stress associated with having the insurance discussions with their insurer was actually much more than suffering through the earthquake itself. So I think that's a real highlight there in terms of the importance of mitigation, is that if you can try and avoid damage in the first place, you can be in a much better situation. Okay, on to the Kaikoura earthquake. Just to reiterate, since a few slides ago, where in the country it is. So as I mentioned before, it was in an area of particularly high seismic activity historically, but it was also in an area where there was relatively low population density. So New Zealand geographically is about the same size as California. However, it only has a little under 5 million people compared to something on the order of 50 in California. And therefore, in the South Island, we have Christchurch here, a city of about 500,000, or close to it anyway, and then Wellington, the capital city of New Zealand, with a similar population, but there's not a lot of population somewhere in between. And so while this earthquake was magnitude 7.8 in size, the actual impacts of this event in terms of direct damage to individual dwellings have been significantly muted relative to the Canterbury earthquakes, and we could estimate that relatively immediately, for example, through USGS's PAGER system right off the bat, telling us that we expect very low fatalities and a moderate amount of damage from this event. One of the, and I'll just touch on these couple of unique aspects in the time that I have left, unique things about the Kaikoura earthquake was really the complexity of the earthquake itself. And so, as I alluded to earlier, this is a particularly seismic portion of the country. You can see here in red lines all of the mapped significant faults in the region. It's an area where there's 4 large strike slip fault systems running through. So this is the Waiau fault, this is the Arbitrary fault, the Clarence fault, and the Hope fault. And so if you're living in that part of the world, you'd expect a large magnitude earthquake would really rupture through one of those faults in its entirety. What happened in this particular case, as you can see there with the fluoro green lines, is actually over 10 different fault segments or fault structures were involved in the rupture of this particular earthquake here. So just illustrating to us again that earthquakes don't always behave as simply as we might want them to be. One example, just looking at the southernmost end of the rupture, we saw some fault offsets looking something like this. I think you can see the couple of people, geologists here, surveying the fault. So we have on the order of about 3 metres of vertical motion at that particular location. There was measurements of up to 7 metres of vertical motion at a few locations, and a little over 10 metres in the horizontal direction as well. Similar to the Christchurch earthquakes, there was some very good constraint from strong motion stations in terms of the ground motions recorded from this Kaikoura earthquake, and the one that I'll just highlight in particular, because I think it's of some relevance to New York as a dense urban area, is the ground shaking recorded in the Wellington region. So as you can see from the larger image there, Wellington was located on the order of about 60 kilometres to the north of this Kaikoura earthquake. And if we look at the Wellington region itself, it's not, other than the size, it's not too dissimilar to New York in terms of it's highly constrained by the geography of the area, being sort of bounded by the ocean. And so the central part of Wellington is located here at the base of the hills, and then we have a series of different reclamations that have occurred over time. And what we saw is, because of that large distance, the ground shaking on rock conditions was relatively moderate. You can see here levels of peak ground acceleration on the order of 0.07 G, but the level of shaking in soil conditions was substantially stronger than that. As you can see there on the right-hand side, factors of 2 or factors of 3 stronger in terms of amplitude. Again, if we look at the same sort of data, but in a slightly different perspective in terms of response spectra, the image on the left-hand side is showing 5 different rock stations, and all of those having pretty similar levels of shaking, whereas the image on the left-hand side is illustrating that amplification of the soil conditions relative to that rock record shown there in red. So based on all that information from evidence of surface rupture offsets from some remote sensing and satellite data, as well as the strong motion records, this is some current interpretations of what the fault looked like, shown there on the left. And then particularly when looking at each of those fault segments, the sort of yellow through black colour indicates how much slip there was on the fault, and as I alluded to earlier, displacements of on the order of 10 to 12 metres across some parts of the fault at some depth below the surface. So this is some ground motion modelling that's been conducted for the particular earthquake. So the rupture started in the south, and you can see that the propagation generally moves in the northerly direction, and if you look closely you can sort of see some of the punctuations in time where different fault segments begin to rupture. And so the progression of this rupture moving northward naturally causes stronger ground shaking to sites north of the fault than it does to the south. And so as this rupture is evolving over time, we're at about 60 seconds now since the rupture first began, we start to see that large amount of energy move north from the tip of the fault into the Wellington region at the south of the South Island, located just here. So as you can sort of see from this animation, a lot of the energy, while it moved in the northerly direction, it also moved in offshore regions. And so when we look at the maximum ground velocity, just one simple metric to decide to discriminate the ground shaking, we see that actually most of the strong shaking occurred immediately off the Kaikoura coast, or otherwise in regions where the population density was relatively modest. As Alan will talk about in some more detail, landslides were particularly predominant in the Kaikoura earthquake, and they really did occur in regions where we identified them to be the most vulnerable. So on the left-hand side there, it's illustrating the actual observed locations of of landslides, and you can see the red colours there indicating the regions with really high density or high severity of landslides, as compared to the image on the right-hand side, which is by inputting the ground motion intensity from the model on the previous slide, how much landslides do we expect based on our predetermined susceptibility. As I alluded to, this is just a snapshot of the landslides, and particularly the one on the right-hand side is at a location called Waiau Point. It's really the most severe of the large landslides that occurred, and you can see if you look to the very right-hand portion of that image that that's actually the coastal road that runs along the Kaikoura coast there. So if anyone's happened to get over to that part of the world, you'll know that that's a really great portion of the country. One of the significant things about that road is that's actually State Highway 1, or your equivalent of something like a Highway 101 throughout the South Island of New Zealand. So you can see this State Highway 1 running here along the coast. Because New Zealand's quite a mountainous region, the benefit of that state highway is it's right beside the coast, it's at sea level basically the whole time, therefore the weather conditions and therefore the resilience of the road to weather hazards is relatively small. Christchurch, as I alluded to, is the largest city in the South Island, and so most of the freight transport travels up State Highway 1, gets on a ferry at the top of the South Island and then across to the North Island to Wellington, and then eventually up to the largest city, Auckland. So 1 week after the event, just as a result of some uncertainty around the performance of the road and so on and so forth, we saw this road closure on the sections there that I've highlighted in red between 1 week to a little over a month. That inland road, State Highway 70, had partial operability in the sense that sort of for 1 hour in the morning traffic could drive from the north to the south, for 1 hour in the afternoon traffic could drive from the south to the north. After about a month and a half, that inland road opened completely, although when there's some substantial rain they have to sort of close it for a couple of hours, and about the same time they actually were able to open State Highway 1 leading into Kaikoura. And so that really allowed now 2 access roads into the Kaikoura region, which was good. However, where the largest portion of those landslides occurred, they currently estimate that it's going to be about 1 year to be able to open that section of road. So because that was previously the main trunk line that traffic would use, particularly freight, then the new route to get from Christchurch to the top of the South Island is via this alpine road, so it has to cross one large alpine pass, a little bit of a smaller alpine pass, and as well as leading to additional time for the journey, there's also some of the consequences associated with a large amount of traffic increase and the wear and tear associated with that. Throw into that mix the fact that because New Zealand's an island in the Pacific, it doesn't have continental weather patterns. So as one example for this, on the 20th of January this year, in the middle of summer for New Zealand, there was a storm that came came across and closed one of the other alpine passes for 5 days and closed one little section there for a couple of hours. And so you can start to see here the huge issues associated with transportation resilience that New Zealand suffers in this particular part of the country. In Wellington City, as I alluded to, there was moderate levels of ground shaking, and so it was a little bit disconcerting to see that 3 buildings were identified as sustaining significant enough of damage not to be an immediate collapse risk, but to require demolition over the subsequent month. And as of the middle of December, about 1 month after the event, there was 11% of the buildings identified as unoccupiable as a result of damage, either non-structural or structural. One of the interesting things about the event actually was because Wellington City was located 60 kilometres away, the short period portion of the shaking was largely attenuated, whereas the longer period portion of the shaking didn't diminish as fast. And so when we compare the red line here, which is sort of the design spectra, with all of the grey lines representing individual recordings of earthquakes, if we average those grey lines, we get this solid black line. So if we talk about some sort of mid-rise building of 10 to 15 stories, we see that the level of shaking was about 2/3 of the design level, whereas for short period buildings, because of that larger distance, the amplitudes were much smaller. And so one of the difficult things to convey here is that all of these old masonry buildings that we have in Wellington City, which tend to be particularly short, they are known as earthquake prone, but because this earthquake was further away, the level of shaking or demand on those buildings was a lot less. And so it was extremely hard to convey to the public this idea that new buildings, which are a lot taller and better designed, were suffering damage, while older buildings which weren't designed weren't suffering damage in any particular way. And so that's something which is obviously potentially an issue for the New York area as well, where you may have earthquakes from some distance away, which cause strong shaking to these very tall skyscrapers, but maybe not such an issue for the shorter masonry buildings. So with that, I thank you for your time, and thanks again to Sissy and all the organisers.